When the Boeing 777 first rolled out, it wasn't just another airliner, it was a gamble. A jet designed to cross oceans with only 2 engines, something no one had tried at this scale before. To make it work, Boeing needed wings that were unlike anything seen on a passenger jet. Long enough to carry its weight, strong enough to bend without breaking, and efficient enough to make the numbers add up. This is the story of the Boeing 777's wings. When Boeing began sketching the 777, they had a challenge. Build a wing big enough for long-haul travel but efficient enough for 2 engines. Up until then, long-range aircrafts like the 747 relied on 4 engines to cross oceans. The 777 was meant to do the same job with just 2, which meant its wings had to be longer and more efficient than anything before. Engineers settled on a wingspan of just over 199 feet for the first models. That number wasn't random. It was carefully calculated to balance lift and drag and gate compatibility at airports. The result was a perfectly judged wingspan that redefined what a twin jet could achieve. Airlines immediately recognized the advantage. The 777 could fly long-haul routes like Los Angeles to Tokyo with fewer engines and lower fuel burn. The wing became its silent powerhouse. At the heart of the 777's wings is its aerodynamic shaping. Boeing used supercritical airfoils which flatten the top curve of the wing. This subtle change reduces drag at high speeds, especially near Mach 0.84, the 777's typical cruising speed. It may not sound dramatic, but over thousands of flights, this design saves airlines millions in fuel costs. Another breakthrough was wing sweep. The 777's wings are swept back 31.6 degrees. This angle reduces drag while keeping stability at transonic speeds. Boeing had refined this sweep angle over decades, but the 777 pushed it further, blending efficiency with comfort. The 777 introduced advanced high-lift devices, including triple-slotted flaps that dramatically increase wing area during takeoff and landing. This meant a plane that was enormous in cruise could also handle relatively shorter runways safely. Combined with raked wingtips on later models, the 777's aerodynamics represented a careful dance between physics and practicality, one that still holds up today. The size of the 777's wings demanded materials that were strong, yet light, like a mix of advanced aluminum alloys, designed to resist both stress and corrosion. At the time, composites weren't as widely used as they are today, so engineers pushed aluminum to its limits. The wing could flex dramatically in flight without cracking or weakening. Flexibility is not weakness, it's strength. The 777's wings can bend more than 20 feet upward at the tips during turbulence or stress. This flexibility absorbs loads that would otherwise shake the fuselage. Internally, spars run lengthwise. Ribs give shape and stringers reinforce the skin. Together, these elements create a structure that's both light and incredibly tough. One of the biggest jobs of the 777's wings is simple: generate enough lift to carry a fully loaded plane across the world, and the wings must do it efficiently. Every inch of drag is fuel wasted. The 777's wings were designed to maximize lift-to-drag ratio. The long span and carefully sculpted airfoil reduced turbulence around the tips, making the wing glide more smoothly through the air. This efficiency translates into longer range and lower costs. On top of that, the wings double as fuel tanks. Each wing can hold more than 23,000 gallons of fuel. That's nearly half the plane's total capacity stored inside the wings alone. Storing fuel here keeps the plane balanced and reduces stress on the fuselage. The combination of efficient lift and enormous fuel storage is what allows the 777 to cover routes like New York to Hong Kong non-stop. Few images capture the 777's engineering better than its wing flex tests. During certification, engineers bent the wings upward more than 24 feet before they finally snapped. That test proved the wings could endure extreme stress beyond anything they'd face in service. In normal flight, the 777's wings flex upward gracefully. This is especially visible from the cabin window, where passengers can watch the tips rise and fall with turbulence. It's a natural shock absorber. Instead of rigidly transferring forces into the fuselage, the wings bend and release energy smoothly. This strength also allowed Boeing to extend the 777 family into heavier versions. The 300ER and 200LR both rely on reinforced wings capable of lifting heavier loads and more fuel. The wings became not just aerodynamic tools, but structural lifelines for the entire aircraft. For passengers, that strength translates to smoother rides, and for airlines, it means reliability mile after mile. But how much can a 777's wings really bend in flight without breaking? Drop your guesses in the comments and we'll come back to this at the end. When Boeing introduced the 777-300ER and 200LR, they didn't just make the fuselage longer or add more fuel. They gave the wings a major upgrade with raked wingtips. Unlike traditional vertical winglets, raked wingtips are extended sections of the wing that taper outward and back. On the 777, these add about 6.5 feet to each wing. The purpose is to reduce wingtip vortices. This improves fuel efficiency, better climb performance, and longer range. For airlines, this meant the ability to open ultra-long-haul routes profitably. For passengers, it meant fewer stops and more direct flights. The 777 wasn't the first to use raked wingtips, but it became the most iconic example of how effective they could be on large aircraft. Building wings as large as those on the Boeing 777 was a challenge, unlike anything Boeing had attempted before. For the first time in commercial aviation, the entire aircraft was designed digitally using computer-aided design software. This allowed engineers to model every part of the wing with incredible precision before a single piece of metal was cut. Spars run the length of the wing, connected by ribs and reinforced by stringers, creating a lightweight but incredibly tough box structure. Massive jigs were used in the Everett factory to hold each wing in place as sections were joined together with thousands of fasteners. Each completed wing stretched nearly 100 feet long and had to be transported carefully across the factory floor before being attached to the fuselage. The scale of this process was immense, but it allowed Boeing to produce wings that were not only enormous but also consistent in quality and performance. Takeoff and landing are where wings truly show their brilliance. The 777 is equipped with sophisticated high-lift systems, including triple-slotted trailing-edge flaps and advanced leading-edge slats. During takeoff, these devices extend to increase the wing's surface area and curvature. This creates more lift at slower speeds, which is essential for a heavy aircraft rolling down the runway. On landing, they extend even further, slowing the plane and allowing it to descend steeply and safely. The 777's flaps are among the largest and most complex ever fitted to a passenger jet. They stretch nearly the full length of the wing's trailing edge. Watching them deploy is like watching gears and panels working together to reshape the wing in seconds. Without these high-lift devices, the 777 would need impossibly long runways to operate. Instead, it can safely take off and land at airports all over the world, proving the genius of its wing engineering. Wings of this scale require constant monitoring and maintenance. Every 777 undergoes regular inspections where engineers check for signs of corrosion or damage from bird strikes and lightning. The wing's design makes inspections easier. Access panels allow technicians to look inside parts without dismantling major sections. Non-destructive testing techniques like ultrasound and X-ray scans detect hidden cracks before they become dangerous. What's remarkable is the durability. The 777's wings have proven to last decades with minimal structural issues. Their resilience comes from both design and maintenance. Airlines around the world rely on them for consistent performance, often clocking tens of thousands of flight hours before major overhauls. This combination of design strength and proactive care explains why the 777 remains one of the most reliable aircraft ever built. Its wings are not just marvels of design, but models of long-term dependability. The latest evolution of the 777's wings is its folding wingtips on the 777X. This is the first time a commercial airliner has been built with tips that fold up like a fighter jet's. Why? Because the 777X's wingspan is enormous at 235 feet with the tips extended. That's too wide for many airport gates. By folding up the last 11 feet of each wing, the 777X can fit into the same gate size as earlier 777s. But folding wingtips are more than a parking trick. The longer span increases efficiency and reduces drag, while the folding mechanism ensures compatibility with existing airports. The system is locked in place during flight with multiple safeguards, making it as secure as a fixed wing. This innovation is a glimpse into the future of aviation. By blending flexibility with efficiency, Boeing has shown how wing design can continue to evolve. The 777X isn't just an upgrade, it's a revolution built on decades of wing expertise. The wings of the Boeing 777 are the reason this aircraft changed aviation forever. They lifted a twin jet into the role of a global long hauler. Very few designs in aviation history have been this ambitious and successful. And to answer that question we asked earlier, a 777's wings can flex more than 20 feet upward during flight without damage. which turns turbulence into smooth motion for passengers. At first glance, Concorde's wings look like a simple and elegant sweeping triangle. But these weren't ordinary wings. They carried 100 passengers across the Atlantic at twice the speed of sound, through shockwaves and intense heat. To this day, the Concorde wing remains one of the most daring pieces of engineering in aviation history. So how do you design a wing that can take a passenger jet higher and faster than some fighter aircraft? Let's find out. The most distinctive feature of Concorde was its OG delta wings. Most airliners use swept wings with flaps, slats, and spoilers. Fighter jets sometimes use pure deltas. But Concorde's designers at Sud Aviation and British Aircraft Corporation needed something in between for a wing that could cruise at Mach 2 and still land safely on a conventional runway. The delta gave inherent strength and stability at high speeds, but the real trick was in the leading edge. Instead of a straight line, Concorde's wing had a graceful S-shaped curve, the OG. This shape generated controlled vortices as air spilled over the wing. Those vortices created extra suction-boosting lift at low speeds when Concorde had no flaps or slats to help. Engineers proved this in years of wind tunnel testing, studying vortex flow with smoke and laser visualization. Variable geometry swing wings were considered, but rejected for their weight and complexity. Concorde's fixed delta was simpler, lighter, and more reliable, and it also took advantage of vortex lift. Test pilots later described it as riding on invisible whirlwinds. At approach speeds of 160 knots, Concorde could still fly safely thanks to this effect. It was a radical idea because passenger jets weren't supposed to behave like fighters. Yet this was the only way to blend subsonic safety with supersonic efficiency. But clever shaping alone couldn't make a supersonic airliner work. The wing needed materials that could withstand the punishing heat of Mach 2. At Mach 2, Concorde's aluminum skin heated to over 127 degrees Celsius, 260 degrees Fahrenheit. Engineers initially considered titanium, which was stronger at high temperature, but rejected it. It was too costly, too heavy, and too difficult to machine for such a large aircraft. Instead, they developed a special alloy known as RR58 aluminum. This was tested exhaustively in temperature chambers, bent and stressed until failure to prove it could hold strength near its upper temperature limit. Even so, engineers knew the structure would expand. In fact, Concorde stretched up to 10 inches during flight. Pilots joked that the cockpit windshield would grow warm to the touch, which was a reminder that the entire jet was expanding around them. This expansion had curious effects. Carpets rippled, cabin fittings shifted, and tiny gaps appeared between panels. Passengers sometimes worried, but the engineers reassured them that these gaps were designed in. When Concorde cooled on the ground, everything shrank back into place. Fatigue management was critical. The repeated expansion and contraction cycle was unlike anything on subsonic jets. Engineers scheduled frequent ultrasonic inspections of the wing structure to catch microscopic cracks early. Maintenance was as much a part of the design as the alloy itself. At Mach 2, Concorde's wings were doing something else most people never realized. Beyond lift and balance, the wings carried a hidden advantage that set Concorde apart from every other jet of its time. What do you think this was? Drop your guesses in the comments below and we'll reveal it in the outro. With materials sorted, engineers started wondering how to make wings and engines work together at supersonic speed. Concorde's 4 Rolls-Royce Snecma Olympus 593 turbojets were powerful, but they couldn't run at Mach 2 on their own. The secret was in the wing engine integration. Each engine sat in a complex nacelle under the wing, with variable intakes controlled by ramps and auxiliary doors. At supersonic speeds, air slams into the aircraft too fast for engines to use. So the intake slowed the airflow from Mach 2 to subsonic before feeding it into the compressors. Sensors monitored pressure every millisecond. Hydraulic actuators moved the ramps in tiny increments, trimming the shockwave at the intake lip. Pilots could hear the system at work as a metallic hum while the ramps adjusted. If it failed, the engine could unstart, violently coughing out flames and thrust. Here's where the delta wing came in. Its shape guided shockwaves perfectly into those intakes, stabilizing them. Engineers called this wave riding. If the shockwave shifted, the engine would surge. But with the wing and intake tuned together, Concorde achieved a remarkable level of stability. The result was an aircraft that cruised at Mach 2 for hours without surging or stalling. a supersonic airliner that could reliably cross the Atlantic in under 3.5 hours. The intakes and wings gave Concorde speed, but slowing it down for landing required an entirely different approach. Concorde's wings had no conventional flaps. Instead, the trailing edge carried elevons, which were control surfaces that combined the functions of elevators and ailerons. At low speeds, the elevons drooped downward, adding camber and helping generate lift. In cruise, they trimmed the aircraft precisely, keeping it stable as fuel shifted and air thinned. The wide delta trailing edge provided the space needed for these multi-role surfaces. Each elevon was powered by redundant hydraulic systems, or 3 separate circuits, so a failure in one wouldn't compromise control. This redundancy was essential for safety at Mach 2, where even small control failures could be catastrophic. Pilots reported that Concorde felt almost fighter-like. The controls were direct with little lag. At Mach 2, even small movements translated to powerful responses. At low speed, the drooped elevons kept the jet controllable. Another trick was the drooped nose, which was not part of the wing itself, but essential for wing use. On approach, pilots needed to see the runway over that long delta. The nose hinged downward, and the transparent visor retracted, improving visibility during landing and takeoff. Form followed function in practically every sense. But even with elevons and a droop nose, the real enemy of supersonic flight was invisible. At Mach 2, Concorde had to battle wave drag. Shock waves formed along the leading edge, and if they detached, efficiency collapsed. The OG curve helped hold those shock waves in place. The thinness of the wing also mattered. At just 3% thickness-to-chord ratio, Concorde's wing was razor slim. That minimized drag, but demanded extraordinary precision in manufacturing. Panels were milled to tolerances of fractions of a millimeter. Even insect residue on the leading edge could disrupt the flow and raise drag. That's why Concorde's skin was polished to a mirror finish. It wasn't vanity, it was necessity. A smooth surface ensured predictable shock waves and minimal drag. Engineers even worried about layers of paint adding roughness and weight. The payoff was astonishing. Concorde achieved a lift-to-drag ratio of 7.5 at Mach 2, which was far better than earlier supersonic concepts, and the key to its viable transatlantic range. But Concorde's most ingenious use of its wings wasn't just aerodynamic. It was hidden inside. Concorde's delta wings doubled as giant fuel tanks. Together with fuselage tanks, they carried over 96 tons of jet fuel. But this wasn't just about storage. The fuel inside was part of Concorde's balance system. At subsonic speeds, the aircraft's center of gravity sat forward. As speed increased through Mach 1, shock waves moved lift rearward. To counter that, Concorde pumped fuel from forward tanks into aft tanks inside the wings and fuselage. At Mach 2 cruise, much of the fuel sat near the tail. Instead of trimming with control surfaces which would add drag, Concorde used fuel as ballast. 11 pumps constantly moved fuel during flight, guided by the flight engineer at his console. He watched gauges showing the levels in 13 different tanks, shifting kerosene like a liquid weight system. Passengers never saw it, but every Concorde crossing was a constant ballet of fuel, moving inside the wings to keep balance perfect. It was a perfect example of engineering turning a necessity into a solution. Then engineers worked on fuel leaks due to intense heat in the sky. On the ground, Concorde often appeared to be leaking fuel. Dark streaks ran under its wings. To many, it looked like a fault, but it was intentional. Because Concorde's aluminum expanded during flight, the tanks couldn't be sealed tight on the ground. Small gaps were left to allow for that stretch. At Mach 2, when the whole jet heated and expanded, the gaps closed and the tanks sealed. The leaks stopped at the exact moment Concorde reached supersonic cruise. Passengers sometimes asked why their luxury jet dripped fuel at the gate. Engineers explained it calmly. Only at twice the speed of sound was Concorde truly airtight. What looked like a flaw was actually proof the design was working. Maintenance crews became experts in monitoring these expansion gaps. Regular inspections ensured the deliberate imperfection never became a weakness. It was another example of Concorde's unique design philosophy of accepting quirks that subsonic airliners never faced. With these challenges mastered, Concorde's wings became more than structure. They became a symbol of daring engineering. Even after Concorde's retirement in 2003, its wing remains legendary. It proved that a civilian aircraft could use advanced aerodynamic tricks once reserved for fighters. The OG Delta influenced later supersonic studies like NASA's high-speed civil transport and today's Boom Supersonic Overture. NASA's X-59 Quest project borrows heavily from Concorde's lessons, exploring thin airfoils and vortex lift for quieter supersonic flight. In wind tunnels today, researchers still analyze Concorde's OG curve as a benchmark. And beyond technology, the Concorde wing stands as a symbol. It wasn't the cheapest solution, it wasn't the easiest, but it worked by carrying passengers at Mach 2 for 27 years. In that time, Concorde flew 50,000 plus supersonic flights. Everyone depended on the brilliance of its wings. So what was that hidden strength of Concorde's wings? It was their sheer durability. Despite flying faster and hotter than any passenger jet before or since, Concorde's wings never suffered a single catastrophic structural failure in 27 years of service. The OG Delta wasn't just elegant or efficient, it was absolutely resilient. If you enjoyed this breakdown, don't forget to like, subscribe, and share for more deep dives into aviation's greatest engineering feats.